transfer in dense particulate flows, fluid particulate flows, and it's a question of the modeling of this interface heat transfer, and also the question of the the velocity temperature correlation. Okay, so my name is underlined just to know that I'm Olivier Simonin, okay? But the people who have done the work, in fact, is mostly Elja Thiam, which is a PhD student, and Enrique Massi, which is a young assistant professor who follows the work. But I was involved. But don't ask me some tricky question. Okay, so just first as an introduction, I told you that I'm doing simulation from 30 years, and this is the list of applications I have performed during this. It's not an extensive list, but you know it's incredible the number of particle fluid flows which can be encountered in industrial application. Okay, and this is the one I have to simulate, and some of them are missing. But you know, it's you have the problem of solid rocket booster, for example, or the problem of coal-fired furnaces, or uranium oxide fluorination, which is a dusty problem. But if you are just doing the simulation, it's okay. And also, as we have seen before, there is a nice new problem like chemical looping process or concentrating solar power. I have also made a very nice experience, which is to apply the modeling approach directly to the problem of the volcanic dome collapse and pyroclastic flows, because in fact the model we used are probably more advanced than the one which are used by the people in this field. On the flow is really a multi-phase reactive flows with a lot of heat transfer, but with some scales which are a bit different. You know, you have some particle of 1 meter of size on the and so on. Okay, so I have some kind of a list of the problem, but I think that everybody here knows about the physical mechanism on what can be the modeling challenge, which are a lot. Okay, as we say with Hans, the more we open doors, the more we find new questions. So it's a problem. I don't know how you will manage in the future, but I think probably we also need to simplify and to try to extract from all the simulations some simplified approach, because I'm always very impressed by the DNS, but every time new phenomena appears, and we don't know how we can account for. So in my presentation, we just focus on the question of energy transfer, which seems to be obvious, but in fact we have not so much information about that. So the methodology we are using is very classical now, and we have some very nice examples here. And we have roughly 3 different scales of simulation. One is a microscopic scale, so the particle resolve simulation. The mesoscopic scale, where you can track 10 million of particles, and you can capture collective behavior. And finally, we want to go to the macroscopic scale. And we are running effectively, as I showed you before, really a lot of application. And I said the scales, we can say about 1 millimeter, 10 centimeter, 10 meter to 10 kilometer. If you are simulating the volcano, then you need to have a large domain of simulation. Okay, so I think that when you are this kind of scale, normally the discrete particle simulation becomes unfeasible, but the complementary of the approach is really very important. So in fact, in my talk, I will skip directly from this one to this one, and I will not pass by the intermediate approach. So this is just the explanation how we can pass from one level to another. And for me, the kinetic equation is important, because it's a tool which allows me to make this change of scale, okay, and to pass from the microscopic to the mesoscopic and finally to the macroscopic scale. And finally, we implement our model in the Neptune CFD, which is a code which is developed for nuclear application, but we have extended to gas particle flows or fluid particle flows. And then we can really apply to a real process. So the tools, I will give a very few details, and if you are interested, there is some a lot of details in the paper of Stéphane Vincent in the JCP. But you know, it's a rough approach, roughly. The specificity is that it's really dedicated to particulate flows. So we can treat the interface equation in a Lagrangian matter because we really know the shape will not be deformed. So it's interesting because it helps us. I mean, it's more, we have no diffusion problems and so on and so on. And also it's, we need to treat the collision, the interaction between the particles. So we need to have this Lagrangian treatment of the particles. So we can include the particle-particle and particle-wall interaction force, and we account for third-sphere collision, and we have also a subgrid lubrification force effect. So the equation set we solve is the one which is written above. And then you have a viscosity which is depending, if you are roughly, it's more sophisticated than that, but roughly we can say that the viscosity is infinite in the solid and is the true fluid velocity in the fluid, but the viscosity is not the same according to the shear and there is some sophisticated implementation. And you have an additional force term, which, for example, account for the particle-particle and particle-wall effect, or you can also use it to if you know the particle velocity, you can force the velocity by a penalty method, okay? So it means that we can use this approach both for unsteady particles which are moving or particles which are fixed by this penalty method. And then we have also a transport equation for the temperature. And in the approach I will show you, we just use a penalty method, and we will force the temperature of the particle. So it's a simple case, so we have used this code in several applications, and I will just show you very briefly some late results. I lie because it's a simple flow. And it's just a quet flows. So it's in this quet flows, so you have two moving walls, and we are trying to analyze the dynamic behavior of the quet flows. So you can compute the mean velocity, you can compute the particle kinetic agitation. In this case, it's mostly uncorrelated kinetic energy. And more interesting, you can also compute the drag correlation terms, which appear in the Eulerian equation. Okay, so it's really interesting, and you can compare these drag correlation terms with the one you can derive from existing model assumption. And for example, it's very impressive, I think, because you have no adjustment of anything. Just by applying the Tenetti et al. Correlation, you can see that the second order drag term and the third order drag terms are very quite well captured by the model. And it's much better than if I use the classical Wen and Yu closure. Then, now we go to the topic, which is more the temperature. So I will go very quickly on this part, just to show you that we have tried to perform some validation of the heat transfer also in the case of a single particle. And we have tested the sensitivity to the number of cells in the particle diameter, to see how converges the prediction. And we have done that in unsteady and steady conditions. So this is just some typical results, for example, for the drag coefficient with respect to the number of cells in the particle diameter, on how it's converging. And the same for the Nusselt number. In fact, we have two values because we compute the Nusselt numbers in a two different way. One from the particle heat transfer and one from the heat balance on the fluid. So normally we should have the same result. It's also checking the accuracy. So finally, if you compare the Nusselt prediction with respect to available correlation and we can see that we have a good agreement, we can say. But the number of cells in the particle is quite large, 80, and we will not use 80 cells in the next simulation. The best agreement is obtained for the Feng and Machiavelli's correlation, but which is also derived from numerical simulation. So sometimes, okay. So most interesting is the fluid flow across a random array of motionless particles with fixed temperature. So it's a classical case now, and you have done this case already, but we will also doing that again. And this is the description of the case. So in fact, I think not very interesting. The only interesting thing is that we play with the mean volume, solid volume fraction, so from 10% to 40%. You see that the grid resolution is quite coarse, 20, it's not so much. And in fact, we have generated random array, and we have 5 different random array for each case. So we can make an averaging on the random array, okay? Okay, so that's, you see that we also play with the Reynolds number. So this is the skip of the flow, okay? So you have the entrance and the outlet, and we want to extract the Nusselt number in a steady state region. So you will show that we will measure it, in fact, in this region. So typically, this is the volume fraction that we obtain if we make an average on the transverse direction of the flow. And you can see that this is the entrance, and then it's quite steady situation, and then it's the outlet. So we will make, when we try to extract the Nusselt number, we will compute between these two planes. Okay, so this is a picture of the temperature field around the particle taken in the middle of the box for a given Reynolds number of a given. So okay, you have it's clear that you have a very strong effect at the entrance, but you have also some very strong effect due to the respective position of the particle, which is a very big problem, in fact, I think, for the modeling. And here you have the picture for the axial velocity field, and so you have some region of negative velocity and positive and some strong acceleration, which naturally will affect the heat transfer. So this is more or less some checking. In fact, it's a total heat transfer rate across the array for the different case and for the different Reynolds number. And what we compare is, again, the sum of the flux computed for each particle with the balance on the fluid flow. So normally the results should be identical. Okay, we are not too far to be identical, okay? Very interesting is, I think, and it is just a question, okay, it's the dispersion of the heat flux. So this is the distribution we found in all our simulation from this is the heat transfer from a given particle to the fluid, normalized by the mean heat transfer. Okay. And you see that the dispersion is huge. So it means that if you want to do Lagrangian simulation, it's a big problem, because normally, in this case, all the particles have the same temperature, and you have more or less roughly the same fluid temperature viewed by the particle. So finally, and we have tried to extract some more representative fluid temperature by playing with the mesh averaging around the particle, and in fact it is not correlated. So it is, the information is not enough. It's clearly, probably it's mostly due to the position of the night-boring particle. So it's really a question of the arrangement of the particle more than a question of the fluid temperature viewed by the particle. So it's really a big problem. Hopefully, in the Eulerian approach, everything is filtered. I don't care. This is a problem somewhere, but I don't care. So I skip to the two-fluid model equation, and in this in this region, we can write the two-fluid model equation in such this way. So you have the classical convective term, mean convective term. You have the diffusion term, which is approximate. It is not very correct, but we check that this term is negligible in our case. You have the transfer from particle to fluid, and you have a correlation, which is not a turbulent correlation because the flow is steady. It's a space correlation. It's because you have an heterogeneous distribution of velocity and temperature. And in the literature, you have two models, which are generally available. One is in terms of the mean fluid velocity, this one, which is the most practical from the modeling, the simulator point of view, because this is the temperature you compute. Normally, you prefer that the model is written in terms of computed variables. But this temperature, this modeling seems to be not so robust sometimes, and people sometimes prefer to write in terms of the bulk temperature, which is in fact the temperature conditioned or weighted by the fluid velocity. Okay, and so naturally you have two Nusselt numbers because both correlations should give the same transfer. You have to be careful of that. You cannot use this bulk number with this temperature. Okay, it's completely wrong. And it's interesting to notice that according to this definition, in fact, there is a direct connection between the difference between the two definitions of the temperature and the temperature-fluid velocity correlation. So in fact, you will say that it's funny because it gives us an information about this flux. So we have compute this number, this bulk Nusselt number from the result simulation, and we have compared with some correlation, okay, from the literature, and in particular with your work. It is this one, no? Sonneto? Oh, no, Dean, sorry. Then. And okay, we can see that the agreement is good. In fact, this is not an error bar. It is the dispersion due to the 5 different random array. Okay, so this is a mean value, but we have 5 different random array, and maybe 5 it's not enough. Maybe the average is more like on that. So it gives you also an error if you want, but it's a statistical error. It is not a numerical error. And we have also computed the standard Nusselt number, we can say. And it's very interesting. We have no true explanation, but it's compared very well with the gun correlation. Surprising, yeah? But it's... and you can see that the two Nusselt numbers, because the scale are the same, in fact, this Nusselt number is much larger. It's larger than the previous Nusselt number. Okay, so we are more or less satisfied because we obtained the same type of result, and we have also identified this question. And the next step is, can we, from this simulation, can we extract some information about the velocity temperature correlation? And in fact, just by definition, according to that and according to the heat flux should be the same, in fact, you can see that the correlation is directly related to the ratio of the Nusselt number. It is a definition result. It is not an assumption, okay? In our case, because it's steady and so on and so on. And then, it's funny because in the Senetal paper, you gave a correlation of this Nusselt number ratio, which is, as you can see, always larger than 1 for our simulation case, and can be about 1.2, so 20% larger. And in fact, this correlation worked quite well with our simulation because, we didn't fit anything. Okay, it's a direct comparison. And so, finally, what we have done, we have said, okay, maybe now we can compare locally, because this was an average analysis. Okay, so now we will see how this fluid velocity correlation is changing in the flow, not at the entrance. My student was too careful. Okay, say it should not work, so he didn't try. So I think it's a wrong idea. You should try, you never know. Okay? Sometimes the models are working better than you expect. So, okay. So he said, no, I compare only in the good region. But these are in fact the temperature velocity correlation measured across the flow. And we compare with the expression given in terms of the ratio of the Nusselt number. We compare with the ratio obtained from the particle result simulation, and it works, and it's logical because, in fact, it's nearly steady, so I'm homogeneous, in fact. The only variable which change is the mean temperature, so it works well. And if we use the correlation, you can see that the agreement is also very good. An interesting thing is that if you look carefully, what happened? If you look carefully to what does it mean, in fact, this correlation change the transport velocity. Because in fact you can add this correlation terms to the mean convection, and it means that the true velocity is the ratio of the Nusselt multiplied by the fluid velocity. So in fact, in the two-fluid equation, I should use not UF as a convective velocity, but nu F divided by nu B UF. So it's 20% larger transport velocity. Okay. So now we say, okay, that's interesting. What happened in fluidized bed? So when it's moving, what results we may have? So it's really preliminary result, but so we have made some simulation of a liquid. It's a fluid particle. Okay, it's a liquid solid, but the ratio between the fluid and the particle is just 8. So it's not gas solid flows. And we have played with the fluidization velocity, and this is a mistake. There is a zero too much, okay? And you can compare with the minimum fluidization velocity. And we choose the prompt number. It's just because we want to have the exchange of heat on the width of the fluidized bed. Because if the exchange is too short, then finally the fluid will be heated in a two row of particles, and then we just fit the prompt number in order that the exchange is on the total width, and we make some simulation with different particle number to see if we have an effect of the height of the bed. And so typically this is the result for one case for two different fluid velocity. And then this is we have some pictures which are similar for the solid volume fraction. So this is an average, okay, of the solid volume fraction at a given time in the axial direction. And in fact, we can again compute a Nusselt number. It's important to realize that I am in the frame of I am in the fluid phase, okay? I'm looking on the average heat transfer from the particle to the fluid. I'm not talking of a Nusselt number of a single particle, okay? Because it's completely different, as we say before, because of the arrangement and so on. And as you see, we can compute both the two Nusselt number, and we have also this difference with a larger standard Nusselt number compared to the bulk Nusselt number. The agreement with the correlation is not so good, but it's not very far. I mean, we don't see some very strong effect due to the fluidization, okay? But there are some, but you know, in fact, I'm interested by industrial prediction. So for me, 50% is identical, okay? No, I understand that if you want to publish in GFM, 50% is 10 papers, but if you are interested to make a simulation of a full industrial process, okay, maybe it's not so important. It depends. And another very interesting thing is to check this model of the temperature velocity correlation. And in fact, even if we are working on some average, and now we are unsteady, and so the assumptions we made before are not completely satisfactory, you can see that the model is working very well, because this is this is the comparison between the two values. If we use the correlation from Sonnet L, it is not excellent, but it is not bad. I mean, we have a good estimation of what is going. Finally, to try to understand what's going on and what is the influence of the unsteadiness, we have made simulation where we take the fluidized bed at a given time, and we froze the particles. So the array is exactly the same than the one we have at a given time in the fluidized bed. Okay? So you can compare the average on this random array, and we have taken several different times, okay, with the one which is obtained in the unsteadiness. In fact, what I want to see is how this inertial effect, in fact, in the flow, will affect the drag or will affect the heat transfer. So it's a nice numerical experiment. And so we have done that, for example, to analyze the modification of the drag force, and we didn't see, for this case, okay, a strong effect. And we have also analyzed for the temperature field. And for the temperature field, an interesting thing is, even if in average, it looks roughly the same. So this is two different fluidization velocities. So we expect more effect when the fluidization velocity is larger. And this is the case. We have the difference between the fixed bed and the fluidized bed of the mean bulk temperature, which increase. And you can see that the fixed bed has a larger exchange coefficient than the unsteady bed. But now we have made another analysis, which is more local. We are comparing the heat transfer on each particle, so at the same position, okay, but the one in the fixed bed and the one in the fluidized bed. And you can see that there is a huge dispersion, which means, in contradiction with what I said before, that the arrangement is not enough to explain what's going on, because the arrangement is the same, but one is steady, one is unsteady. So in fact, unfortunately, it means that the local heat transfer coefficient for a single particle is depending on the history of the particle. So that's awful. So I hope it is not crucial in average, but it's so that was the point I said before. Each time you open a new doors, then you have the next one. And so, okay, for Lagrangian simulation, it's a problem, because how to account for that, and are we to account for that? It's also a very good question, okay? Because we have to wonder if, when we are dealing with DAM, are we really tracking physical particle or numerical particle? That's a philosophical point, as said before by our friend. So it's finished. That's my conclusion. It's just, I say enough about it. It's very impressive to see how this particle result simulation can help to understand what's going on locally, or also to try to develop some closure model at the macroscopic scale, but this is not original. I think all the workshop is demonstrate the power of this connection, of this utilization of numerical simulation at different scale. And the second is, concerning to heat transfer, my case is very simple, because all the particles have the same temperature. So what happens if you start to have a different temperature, and the next step for us should be to make a source term in the temperature. So at this time, the temperature is no longer a fixed value, but become a result of the heat transfer. So it should be interesting to see how we can extend, use, or just push away the correlation we have obtained. Thank you very much.
Thanks very much, Olivier.